You,
Hi everyone. Welcome to the Involving Intelligence seminar. It's our pleasure to have Paul Liang here. So Paul is an assistant professor at MIT Media Lab and MIT ECS. His research focuses on building multisensory AI that can learn from text, speech, video, and real-world sensors and many other modalities to enhance the human experience. And today he's going to talk about the foundations of high-modality multisensory AI. Let's welcome Paul.
Thank you. Hi, everyone. It's a pleasure to be here. Thanks for coming. So I'm really excited to present some of our latest research on the foundations of high-modality multisensory AI. For some context, I recently finished my PhD at CMU. I was a visiting researcher at UC Berkeley and just started a new research group at MIT this past semester, last month. And our new research group is called Multisensory Intelligence. And the whole vision of our research group is to develop human AI symbiosis. And what I mean by that is we're an AI research group. We develop AI tools, but the whole goal is to build AI that doesn't just replace humans, do what humans can do, but rather lead to some symbiosis between humans and AI. How can humans and AI come together to create something that is more than just AI alone and humans alone? So we're all driven by this passion towards creating human AI symbiosis. But to create human symbiosis, we got to do that across different scales. How do you build an individual level AI? How do you build a single AI to understand a single person and interact with a single person? All the way to a population scale. How can AI be able to interfere and interact with the whole population to lead to better outcomes in some society? We also do this symbiosis across different sensory modalities. Language is a great medium for us to communicate with AI. We have ChatGPT, we have language models. Language is a great medium. But us humans, we integrate more senses than just language. We use our visual expressions, we use our voice, we use smell, we use taste, we use touch, all these different sensory mediums to better understand the world around us. So a lot of our research is also about enabling new forms of interaction between humans and AI beyond language and language models. And finally, the whole goal of this is to make sure that humans are more productive. We can be more productive in our daily experiences, in the workforce, in schools. We can be more creative, coming up with new creative ways to express ourselves, and finally to improve our well-being. And I'm going to cover all of these applications in this talk. And in order to enable that, our group works on three main directions. So our first direction is building the foundations of multisensory AI. How do we build this new generation of AI systems that are able to learn and interact with the world through many sensory modalities beyond just language? Our second big theme is enhancing the human experience. How do you actually put this AI into human lives, actually use that to interact, to sense, and to learn with humans to lead to better outcomes? And finally, as we build all this AI to improve and understand humans, how can we make sure this remains robust in the real world? So this involves understanding all these questions surrounding bias, surrounding fairness, maintaining the privacy of our personal data, and making sure that all these systems that we deploy isn't just for the Western world, but are multilingual, multicultural, and multisocial in nature. So those are the three pillars that really drives my research and the research in our new research group. And I can't go more without showing a photo. This is a new photo that we took in front of MIT's dome just last week. We're new, but we're starting really strong. We have a large group of students. Half of them are working on the theoretical foundations of multisensory AI. So what are the scientific principles to design AI systems that are able to learn and integrate many sensors in the world? And that's half the group. And the other half of the group is working on various applications of multisensory AI. Some of them are trying to integrate that into education. How do we better teach and educate students, not just using language, but using language and vision as a medium? Some other students are applying it towards creativity. How can we develop AI systems that can help humans generate not just art, but also art with music, with dance, in historical context, with different cultural contexts together? And we have a ton more students working on various applications in our group. So if you're interested in multisensory AI, definitely come talk to us. I'm sure there's different ways for us to collaborate and engage with each other. So what is multisensory AI? I've talked about it at a very high level, but the whole goal is to build AI systems that can actually learn and interact with this multisensory world. We've seen great progress in language models. They understand only our spoken words. But how can these language models also understand our vocal expressions? The way we say things and the gestures we use, such as pointing or showing anger and sadness when we're expressing our intentions. A lot of our work is also in the medical space. How can we build AI systems that understand a human's health, not just through X-ray images in radiology, but also through all these other sensory modalities such as microscopic images, ICU sensors, daily sensors, such as wearable devices, to holistically understand a person's health and well-being. And that's just a glimpse of all the modalities that we have that humans can interact with in the world. So our whole goal is to build AI systems and expand the frontier of what AI systems can perceive and interact with across all these senses. And I'm going to start with some applications. I've talked about healthcare a lot, but a big vision of ours is to build AI systems can really holistically understand a person's health. To understand our health, we need to understand our physical conditions. So over here, I'm showing an example of some of our students' projects. On building these systems, they're able to sense the status of patients in the ICU. So you're showing all these object recognition systems. They're able to recognize everyday objects, such as a bed, a patient, but also objects that are specific in the medical context. Is this patient wearing slippery socks? Is this patient hooked up to an ICU machine, which is reading at invasive sensors? Is this patient actually being helped by a nurse as they're getting up from the bed and onto a wheelchair? So these are indicators of physical health we're looking at. We're also looking at indicators of personal emotional well-being. How is a person feeling at any moment in the day? Are they happy? Are they sad? And all of this can only be observed if we have inferences on what a person says through language, but also what a person is expressing through their expressions and how they're saying these. So building state-of-the-art facial recognition and facial understanding devices that can understand emotions that are expressed through their face, and these emotions in the context of what the person is actually saying. And finally, we're doing all this in the context of social wellness, how a person's mood and well-being and their physical health should be understood in the context of their social interactions. Am I making friends? Am I interacting with many people? Or am I isolated just in my room the whole day? And we personally believe that all these multimodal indicators will come together, whether a person's physical health is a big influence on their daily mental and emotional well-being, and their mental and emotional well-being is a big indicator of their social interactions, and their social interactions also determines how much physical activities and physical influences they're having. So a big part of our application is in health and wellness. And before I get into the technical details, I also want to show some other interesting applications of our work. Some of the coolest applications I'm really excited about is that of smell. How can we design a new AI system that is actually able to smell just like how we smell things? So over here, I'm showing you a video where we've developed new smell sensors. And if I bring the smell sensor close to an object of interest, it actually recognizes that this is coffee with milk. And you can then relay this information in real time to a large language models, which has all these reasoning capabilities of how many calories this might have. If it's whole milk, it has this number of calories. If it's skim milk, this number of calories. And whether you should drink this at night before you go to sleep. So this can be seen as a personal assistant that uses smell as a sensory medium to better understand the world, understanding what you're eating and drinking, and use that to influence how you're behaving. I'm showing another example here, which is a smell sensor. Again, our line of work and building AI that can actually smell peanuts, right? Peanut is a big allergy for different people. And if you bring it towards these candy bars or peanut butter, it can actually sense that there's a presence of peanuts within these mediums. And then you can use, is this safe to have an allergy? And you can tell the language model, I accidentally ate this. What should I do? Who should I call? How should I treat this allergy? So these are just examples of some of the work that's happening in our group to really expand the mediums in which AI systems can interact with humans and interact with the world. So in the bulk of this talk, I'm going to cover some of our recent work towards actually achieving this capability in current AI systems. And if you look at the current progress of AI, we have lots of interest in multimodal AI. We're trying to build systems that can integrate language with speech and gestures, collect all these modalities in parallel, and build systems that can make predictions about the human who's actually saying and expressing these behaviors. For example, what's their sentiment, what's their emotions, whether they're being sarcastic or humorous, and so on. And there's been a great progress and demand towards these multimodal systems. In particular, there's demand for systems that are able to take in more modalities in input space. I'm just looking at language, speech, and gestures as input, but it might make sense to take in physiological sensors, your heart rate, your blood pressure, your interaction with other people. Or even try to build AI systems that take in more and more modalities as input. There's also increasing demand for systems that are able to predict more tasks in the output space. Let me show you an example of predicting sentiment and emotions. But you want to build a system to be able to ask and answer any questions about my social interactions. You might want to build this system not just for people in the Western population, but also for people in all the other populations in the world. So there's more demand for different tasks and capabilities of these AI systems. And this is all great, but this leads to very natural problems. One of the biggest problems we're studying is that of a data bottleneck. You can take all the text data that you want, but there's going to be a lot more text data than the amount of data with text paired with images. There's going to be a lot more image-text pairs than data with text, video, and audio, and a lot more even with text, video, audio, and medical sensors. So the more modalities that you try to sense from the world, the less data you have. That's natural. Another big issue is this modeling bottleneck. We have great systems that are able to work with language and language only, but if you want to try to build these systems to take in more and more modalities, they start running into bottlenecks such as difficulties in scaling to many modalities, difficulty in scaling to long sequences, difficulty in scaling to very sparse, missing, and perhaps even continuous data. So you have a ton of issues as you try to scale these systems to more and more modalities and tasks. And therefore, in today's talk, I want to highlight this vision of ours, which is a big research effort in our group, towards building towards high modality multimodal learning. So the word high modality here is very intuitive. How do we build systems that can actually scale to more and more modalities as we collect more data? And the key insight between some of these high modality systems is that if you just have one data set, you just have those modalities and that task observed for that data set. But in fact, the whole world can be seen as different multimodal problems. You also have images and text. If you look at multimedia data, you also have images and sensors. If you look at robotics data, you also have sensor data and tabular information if you look at medical data, and so on. Right, the whole world can be seen as a partially observed multimodal problem. Each task that everybody is working on here within the ML and AI space should be part of this high modality effort. They show us partial subset of input modalities, and they show a partial subset of the tasks that we're trying to predict. And therefore, high modality learning, the goal of high modality learning is to build multimodal AI over all of these diverse input modalities and prediction tasks, given only these partially observable subsets. How do you build a model over the union of all of these inputs and outputs that we see when we collect data? And I personally think this is very important. I personally think this is a pathway towards building foundation models that are actually grounded in real-world sensory modalities, going beyond language models to language models that are actually grounded in what they see, what they hear, what they touch, what they smell, and so on. It's also a pathway towards more general purpose AI that is both multimodal in the input space and multitask in the input space. And this has great implications, whether you're working with low resource data, whether you're working for a low resource language, or for a task nobody cares about, this is probably the way to go. But of course, this doesn't come without its challenges. And therefore, in today's talk, I want to highlight some of our work towards tackling these challenges. There's two fundamental challenges. One big challenge is that of interactions. You're going to build these partial data sets and going to train models over all these modalities, but which modalities are actually going to interact with each other to give rise to new information? Over which two modalities would fusion actually be beneficial? That's the first challenge. The second challenge is that of heterogeneity. We're going to start building AI over very, very different input modalities. They're going to be very heterogeneous, very different in nature. How can we actually tackle the engineering challenges of building systems that can scale with very different inputs? So therefore, in today's talk, I'm going to cover both of these challenges. In the first part, I'm going to cover some of our work and really understanding these multimodal interactions, figuring out when modalities from very different sources will interact to give rise to new information, and how we should be modeling that fusion to give rise to new information. We're also going to cover some of our work in heterogeneity. How do we actually build the science, engineering, and benchmarks towards scaling these systems to very different input spaces? All right, so first of all, foundations of multimodal interactions. So, at an intuitive level, multimodal interactions describes how modalities combine to give rise to new information for a task. I'm going to use these Venn diagrams as an example. So, Venn diagram of modality 1 in red and modality 2 in blue. And I'm purposely showing these two Venn diagrams as having some overlap and having some unique information. That's the most general case, right? If you think of images and captions, your caption will describe your image to some extent, but there's always something in the image that isn't described in your caption, and there's some information in the caption that isn't represented in the image. I'm going to use a third circle Y to represent the task you're trying to predict. And intuitively, there's three types of interactions we care about understanding. The first interactions are redundancy, where there's some common information between both modalities for your task. So imagine I'm saying something positive, like this movie is great, with positive, happy, laughing expressions on my face. And because both those modalities indicate that I really like the movie, using both modalities, you can be very confident that I love the movie. The second type of interaction is that of uniqueness, where there's some unique information in one modality important for the task, but not present in the other one. So for example, saying something slightly positive, like this movie does a good job developing the characters with mostly neutral facial expressions. And out of these, one of the modalities has the important positive information for the task, and the other one has no information. And the final case, the one that I'm most excited about, is that of synergy, where there's some emerging information that only arises when you fuse both modalities together. So imagine saying something positive, like wow, but with angry or frustrated expressions. And you can actually infer that it's the difference between these two modality signals that indicates that the person was actually being sarcastic about the task. So the first part of this talk is going to cover, how do we mathematically formalize these intuitions? How do we formalize actually what information is redundant, what information is unique, and what information is synergistic, so that we know which modalities will actually come and fuse together to give rise to more information. And formally, I'm going to define this as some joint distribution P. So this joint distribution is going to be over your two modalities, x1, x2, and some label y. And together, both of these modalities give some total information to the task. And the goal is to decompose this total information into how much of it is redundant, unique in the first, unique in the second, and synergistic. So to enable this decomposition, I'm going to cover two key ideas. The first key idea is that if you have this joint distribution over your both modalities in your label, there's two other very important distributions that you can also infer. So we call these unimodal marginals. That's a distribution over x1 and y. So you're marginalizing x2 away, and a distribution over x2 and y. So you're marginalizing x1 away. And the key idea behind these marginals is that redundancy and uniqueness are encoded within these marginals, but synergy is not. And that's going to give us a path towards separating how much synergy there is from how much of other redundant, unique interactions there are. So why is that the case? So let's go through some examples. Let's say x1 was positive, you're saying something positive in language. x2 was positive, you're showing something positive in your expressions. And because both of these unimodal marginals are the same, you get a sense there's redundancy in your data just by looking at these two different marginals. The second case, you're showing something positive in language, you're showing something neutral in your facial expressions. Just by the sense that these two marginals are different, you get a sense that there's uniqueness in your data. But this logic fails for synergy. You're showing something positive in your expressions, wow. You're showing something negative in your facial expressions, angry or frustration. And without knowing the true multimodal label, you can't distinguish whether it's unique or synergistic. If the true label is positive, then it has unique information in the first modality. If the true label is negative, then that's unique information in the second modality. And if the true label is something completely different, like sarcasm, only then is that synergy between your modalities. So just from the unimodal marginals, you can infer how much redundancy and uniqueness there is, but you cannot do so for synergy. And that basically means you can combine these unimodal marginals in a way that keeps the same amount of redundancy and uniqueness, but at very different amounts of synergy. In the first example, you can combine this marginal to get a joint distribution. We're given both language and vision. You inherit a positive label. And because that's the exact same as the original distribution that you started with, that means redundancy contributed to all the information, and there was nothing else. In the second case, you could create a joint distribution with given both modalities. You inherit the positive label from the first modality. And because that's exactly the same as your original joint distribution, that means uniqueness contributed to all the information and nothing else. But in the synergy case, you could create a joint distribution where given both modalities, the label is either positive or negative, but this is going to be very different from the actual distribution that you started with, which is that a person was being sarcastic. And because you're losing so much information when you only combine these unimodal marginals, all the information that you lost was the amount of synergy between your two modalities. So formally, what we did was that we started from some joint distribution P over your two modalities and your label. We inferred a marginal over your first and a marginal over your second modality. And we considered all these intermediate joint distributions Q. These are joint distributions over x1, x2, y, which satisfies the fact that Q of x1 and y is equal to P of x1 and y, and Q of x2 and y is equal to P of x2 and y. So the marginals of Q are the same as that of P. The only difference is the overlap between x1 and x2. Right? Enforcing these marginals is important because it keeps the redundant and unique information the same, and the only difference is the amount of synergy across the different Qs. Therefore, you can find the distribution in Q that has the least total information, that keeps redundancy and uniqueness the same, but minimizes synergy to 0. You can compute the total information in P, which is redundant, unique, and synergy, which means that synergy is the difference between these two terms. And you can prove this. You can prove that this Q star that you obtain from this minimization problem is actually a distribution with 0 synergy, because you get S of Q star is equal to I of Q star minus this minimization problem. You get I of Q star again. I of Q star minus I of Q star cancel out. You get 0 bits of synergy in this Q star distribution. So that's the end of the math. So essentially, here's a way of formally defining synergy. Intuitively, you can think of it as the total information both modalities contribute towards the label minus the worst way of combining my two individual modalities, because this worst way essentially minimizes the synergy to 0. And in fact, we show that we can actually estimate these terms pretty efficiently in practice. This is a total information term. This is a minus mutual information term. You can rewrite minimization of mutual information as a maximization of entropy. You're essentially saying, how can I find a distribution that is the worst in predicting a label, that is the highest entropy in predicting a label, subject to these constraints, subject to the fact that your Q distribution respects the unimodal marginal constraints. And for those who are mathematically inclined, you realize that if your modalities are small and discrete in support, this is basically a convex optimization problem. Your objective is the maximization of a concave function, so it's a convex optimization problem. Your constraints are linear constraints over your optimization variable. That means with any convex solver, you can solve this exactly in a matter of milliseconds, very fast. If your data modalities are high dimensional and continuous, then it might be harder, because you can't really put these continuous distributions into convex optimization solvers. But in our paper, we show that there is an approximate estimator. You can essentially embed this optimization function as an objective into a neural network and solve this problem approximately. So several key ideas here. First of all, it's very efficient. You can essentially approximate these quantities to understand how much redundant, unique, and synergistic information there is in a multimodal distribution. And that can be very useful as a precursor to understanding your data, to choosing models and optimizing your multimodal models. Secondly, I talk about all this in the context of information theory, but information theory is just one way to formalize it. You don't have to use information theory. You can get rid of some of the math. You can use things like correlation, linear probing, and so on. But the same idea remains. Synergy is the amount of total information your two modalities contribute towards your label minus the worst way, some worst way of coupling, fusing your unimodal marginals to predict the label. And in fact, in subsequent work, we went a step further. Some of you might notice that synergy requires your full distribution. You need a joint distribution, or at least supervised and paired samples over x1, x2, and y to estimate, while redundancy and uniqueness can be estimated only from the marginals, using only x1 and y, and using only x2 and y. And in subsequent work, we've shown that you can actually relax this assumption on synergy. You can obtain new lower bounds and upper bounds. So these are bounds, they're approximate, they won't be exact. And these lower bounds and upper bounds depend only on the marginals. So one intuitive lower bound for synergy is if I have a model on my first modality, x1 to y, for example, a language-only model, and I have a second model on my second modality, say a vision-only model, and then I can compute my disagreement between these two models. So how much does language tell me that is very different from what vision tells me? That can actually be a lower bound on synergy. And we also show that an upper bound can also be computed in a similar way. If I have a language-only model and I have a vision-only model trained separately, initialized from pre-trained models, I can essentially find the best way in which these two models overlap. That's called a maximum mutual information, or conversely, minimum entropy coupling of these separate unimodal models. And that gives you an upper bound, the most ideal upper bound on how much synergy there could be. And this is great because now you can compute these lower and upper bounds using only the marginals, using only language models and vision models without training a multimodal model, a vision language model to begin with. So that looks like this. If you have all these different data sets, you might have a language model on your language, you might have a vision model on your gestures, and let's say you just train a sensor model, only on sensor data. Even using only these unimodal marginals, you can infer how much synergy there could be when you fuse these two modalities together. All right, to show some results. We did a lot of experiments. We essentially tried to look at how accurate these estimators were in identifying the types of interactions in your data. So in the first setting, we looked at videos of humans expressing themselves. They were saying something through language, and at the same time, they were showing facial expressions and vocal expressions while expressing themselves. And the goal was to understand their sentiment, so whether they were happy or sad in these videos. And if you run these estimators, you'll find that there's a lot of uniqueness, a lot of unique information in language, which makes sense. We say positive things, and we say negative things. But the second most important interaction is our redundancy. So these are settings where you're saying something positive while showing positive expressions and vice versa. And a lot of this evaluation was done with human judgment. We got lots of humans to look at these videos to interpret how the humans in these videos were expressing themselves and to come up with human judgments of what these interactions should look like. And because of this pattern of interactions, you can actually suggest using a language-only model will capture all the unique information in language. But if that isn't enough, you should build a model that enforces the agreement. Essentially because language and vision are telling you the same thing, the same redundant information. Another example, we looked at the same modalities, the spoken words of a person, and their audio visual expressions, but now we're trying to tell whether a person is being sarcastic in these videos. So this is actually obtained from the Big Bang Theory. If you watch that show, it has tons of examples of Sheldon, Leonard, all being sarcastic with each other. And we again find that there's lots of unique information in language, which makes sense. They say sarcastic things. But the second most important interaction now is synergy. So there are actually a lot of examples where you're saying something which seems to be positive in nature, but based on the context of how you say it through your expressions and your voice, it should be interpreted as sarcasm. So one example here is that Sheldon is saying, it's just a privilege to watch your mind at work. And because he's putting emphasis on privilege, you can tell that he's actually being sarcastic, and it's not actually a privilege. We've also applied this to several other settings in the medical space. So one of these applications was working with psychiatrists at UPMC, University of Oregon, and Columbia. And we've been tracking young teenagers at a risk of depression. So these are 18-year-old teenagers. There's a control group. There are people at risk of depression, and there are people who have been diagnosed with depression. And they've kindly given us access to their mobile data. So the different data sources that these teenagers are actually typing and using their mobile phones throughout the day. And the goal is to understand their daily mood. So we actually find there's actually a lot of synergy between the modalities that they're using on their phones. If you look at the text they're typing, so they might be typing some positive words like love, thanks, and haha. They seem positive in nature, but if they type very quickly, that's a big sign of positive mood. If they type slowly, if they type it, delete it, hesitating, typing it very slowly, that's actually a big sign of negative mood. Another example, they're typing some words like don't and just, they seem negative in nature. If you're typing it very quickly, it's a sign of negative mood, but if you're typing it slowly, with deliberation, hesitancy, that's a big sign of neutral mood. So these are some examples how we've been able to uncover these interactions between modalities. They're currently being used by some of these psychiatrists to study the mental health of their patients. In physical health as well, we've been working with folks at Harvard Medical School to understand different indicators of cancer. So one modality are these histology images. So these are microscopic images of tumor cells and where they're invading or nearby to healthy cells. And the other modality are genomics. So different gene expressions, proteins you can obtain from blood tests from these patients. And the goal is to understand risk. How long can these patients hope to survive from the cancers that they have? And we actually find that different cancers exhibit different interactions. Glioma, for example, it's a type of cancer in the brain, is predominantly consisting of unique information in genomics. Whereas pancreatic cancer involves a ton of synergy between the genomes within these tumor cells and visually where these tumor cells actually are and whether they're attacking nearby cells. And therefore, if you do multimodal modeling with pancreatic cancer using both modalities, you get a ton of performance boost. But if you try multimodal models with glioma, brain cancer, you don't get any performance boost at all. This is good because, it was able to explain to doctors why it was that sometimes multimodal models work and why sometimes they don't. So that's part one, the bigger part. Understanding how modalities interact with each other to give rise to new information. We looked at how we can define it formally through information theory. And we also talked about how we can practically estimate some of these information theoretic measures in practice and inform what data to collect for which applications. In the second part, we're going to look at this problem of heterogeneity. A lot of times we're trying to build models that go beyond two modalities, as we've talked about in the first part, and really build models that can take in many, many different input modalities that are very different in nature. So in this part, I'm going to cover some of our recent work towards that. As I mentioned, a lot of this world, the whole world around us can be seen as a partially observed problem. We see certain modalities when interacting with humans. We see modalities when working with the internet, multimedia data. We see modalities when treating robotics and so on. How can we build general purpose systems that's able to take in all these very different input modalities and predict very different prediction tasks? So our key idea is to really scale up some of these multimodal transformers. And at a first order approximation, despite these modalities being very different, they can be seen as sequences. It's a big approximation, but it's something we're comfortable making because it allows us to really scale these models by treating different modalities as sequences. You can treat language as a sequence of words, speech as a sequence of time steps, treating sensor data as a sequence of readings. You treat many modalities to a first order approximation as a set of sequences. Once you treat them as sequences, you can apply modality embeddings. So that essentially captures that language is present in the first data set and also present in the second data set, and so on. You can apply unimodal transformers that captures the interactions between one part of the modality and other parts of the same modality. So words with other words in a sequence, pixels with other pixels in the image. You can apply multimodal transformers. So this captures redundancy and uniqueness. This captures how different modalities pairwise interact with each other. By the way, we invented multimodal transformers, so check out that paper And you can apply task-specific classifiers to train for different tasks at the same time. And because we're doing multimodal and multitask learning, we're going to train this whole model with the same set of input modalities, same set of unimodal encoders, same set of multimodal encoders across all these different tasks. So what do we train it on? So we actually created a lot of benchmarks. We created a bunch of benchmarks in the multimodal space that essentially put together all these different tasks, right? Tasks from robotics, health, HCI, multimedia. We've put all of them together. We've standardized it so that you don't have to pre-process it. All this code is available. And this essentially covers, to our knowledge, the largest set of input modalities that there currently is in one benchmark. We've also implemented all these baselines, so you don't have to. We call it MultiZoo. It's a zoo, a model zoo, that essentially take in different methods of pre-processing your data, defining unimodal models, defining different ways to fuse your modalities, different ways of training, whether it's supervised learning, contrastive learning, and different ways of optimizing it. Again, so you don't have to. It includes 20 recent models, but because we're doing it in a compositional way, you can mix and match, so you can get more than 200 combinations of any state-of-the-art paradigm model in multimodal learning. And those are our baselines. Previous baselines would just take different input data sets and train separate models. You have a model for multimedia, you have a model for robotics, you have a model for healthcare, and so on. And this graph, what we're showing over here, on the x-axis is efficiency. So if you add up all the parameters in these specialized models, what's the total number of parameters it's using? So to the right is better, more efficient. And on the y-axis is performance, average performance. If you average all the performance of these specialized models, what's the average performance? So higher is better. And blue dots essentially show all these combinations of models, more than 10,000 combinations. And red shows the Pareto frontier. So models that are neither dominated in performance or dominated in efficiency. So that's essentially the state-of-the-art frontier of all these specialized models. And what we're proposing essentially is this high MMT. We call it high-modality multimodal multitask model. One model that is able to take in all these input modalities and predict all these prediction tasks. And if you run it, you get this point. You get something that's very efficient for sure. You're essentially sharing parameters because you're designing a single model across everything. You're no longer adding up all these parameters, you're sharing parameters. So it's very efficient. That makes sense. And in performance-wise, it's reasonable. It's something that is within the range of state-of-the-art performance. It's not the best, but it's also not terrible. And with that, we've seen two extremes. We've seen an extreme where you're doing extreme specialization over everything. Every task is different, classic supervised learning. And you're seeing a task where we're really pushing the limits of parameter sharing to the extreme, one model for everything. And a natural question to ask is, what's the right balance between these two? How much should we be sharing parameters versus specializing models for different tasks? And one intuitive idea we had was to naturally to quantify how similar and different these modalities are. You could train a model on a first modality, for example, language, and you could essentially tell whether this language model transfers to other modalities. That tells you whether language should be encoded in the same way as images, in the same way as sensors, in the same way as medical data, and so on. But essentially measuring which modalities are similar to each other. And that can inform you how much you should be sharing unimodal parameters. Modalities that are similar to each other should share parameters, and modalities that are different should have separate parameters. And the same thing for fusion. If I train a fusion model between two modalities, for example, language and vision, does the same fusion model transfer to other pairs of modalities that I might want to fuse together? Some of them will transfer well, in which case you would share parameters. There'll be a fusion, multimodal fusion parameter sharing. And for those that don't transfer well, it should not be sharing parameters. And in practice, very efficient. Essentially saying if I take these unimodal models that are pre-trained, language models, for example, how well do they transfer to other modalities? And if you do that, some very interesting patterns emerge. We see that a first group of unimodal modalities, they all transfer very well to each other, are essentially this group of temporal modalities. modalities that have a temporal structure. So language with words across time, speech with words that you're saying across time, sensors with sensor readings across time. All these one-dimensional modalities, we actually find that can be encoded by the same set of parameters. But this wouldn't transfer very well to the second set of modalities, which are more spatial, 2D in nature. So these are gestures, facial gestures, vision and robotics, vision and multimedia, vision and HCI that have two-dimensional structure. And yet again, these don't transfer to the third group, which are structured tables and sets. These are modalities such as tabular data, set-based data, which have individual entries, but where there is permutation and variance within the entries of your tables and sets. So that should be a third set of parameters. They don't transfer well to the first two sets. And that's very natural, a very natural grouping obtained from this data-driven method, 1D data, 2D data, and also permutation and variant data. And on the fusion side, we find that vision and language and vision and speech fuse very similarly with each other. So you can use the same set of parameters, but otherwise, there's a lot more differences in how modalities are fused than the modalities themselves. So you should be opening up more separate parameters for the fusion between modalities. And if you do that, and you train this model, you get a very nice trade-off. You get these yellow stars, which essentially allow you to control how much parameters you want to use based on how much parameter sharing, while at the same time achieving much better performance than these previous fully shared or fully separate models. So we call that high MMT, high modality and multitask multimodal transformer that is heterogeneity aware. It is aware of the similarities and differences in the input modalities and output tasks. So to summarize, I've talked enough. In the first part, we discussed this problem of interactions. How do we learn which modalities are interacting with each other in which ways? Whether there's some redundant, overlapping information, whether there's some unique information that a modality provides. And the coolest case, when is there synergy between modalities when they are fused together? We used information theory as a way to formalize these interactions. And the second part, we look at heterogeneity. How do you go beyond two modalities to actually build systems that are able to learn from a larger range of sensory modalities in the world? We cover some of our benchmarks like MultiBench, MultiZoo, giving us a good platform to work on. And also we cover some of our work in these high modality models that really leverage parameter sharing to the extreme to learn from these many modality, many task scenarios. So a ton of things I'm excited about, ton of open questions. How do you build up a better foundation for these multisensory models? How do you build systems that are still leveraging these foundation models? We can't deny the impact of vision, language, foundation models. But if you want to encode real-world data, many of them are tabular in nature, sensor, high frequency, long range in nature. How do you build the right foundation models with tabular data and sensors? I'm also thinking nowadays a lot about this problem of dynamic modalities. A lot of the settings that we've seen today have settings where you have modalities presented to us upfront. These are the three modalities you're going to work with. But in many real-world settings, in medical, for example, you're going to a doctor's office, you've taken an X-ray, and the doctor's always thinking, what modality should I collect next? So how do you discover what's the right next modality to collect the right information while reducing computation costs? And finally, a lot of our group is working on agents, building multimodal systems that doesn't just perceive the world, but can actively interact and influence the world by taking actions. And I'm excited to discuss that with folks here as well. And with that, I'd like to end the talk. Happy to take any questions about what I presented today, or more broadly, the work being done in our group. Thanks, everyone. Yeah.
I have a two-part question. The first is trying to take away from some of the earlier discussion around synergy, and it is the case that you approximate this and said you have different files here, and we have the actual modality. And then the second question is figure out the dimensional modality or rather training this dimensional modality. I was just curious about how you put that added to the So then it realized it works. Can we see that it'll like contact your and how we get out
Cool. So first question. So for synergy, we're not saying that as long as you have unimodal data, there is going to be synergy. There are still some things you're going to compute. You gotta basically take x1 and y, so that's your language only model, x to the y vision only model. Go compute these lower and upper bounds, and that gives you a proxy of how much synergy there would be if you had combined these two modalities together. The intuition of the lower bound is that if your two modalities predict things that are very disagreeing with each other, then something cool is going to happen when you put them together. And the upper bound is if you put these modalities together and there's possibly high mutual information in their overlap, then again, something cool is going to happen when you put them together. So it's not just if you have the unimodal marginals, there are still some statistics you got to compute to infer how much synergy there is. For the second part, how do we tokenize tabular data? It's pretty straightforward. We just took all the entries and serialized them. Didn't do anything fancy. I'm excited about what the next frontiers are. I personally have some students working on that. How do you essentially combine, a lot of the best state-of-the-art methods for tabular data are not based on deep learning, right? Gradient boosting, decision trees. How do you combine that with deep learning on language and vision, which clearly works state-of-the-art? We don't have an answer to that yet, but I personally believe it's going to be some hybrid between these two models. But as of this, it was mostly just pushing the limits behind what can you do as a first order approximation of just serializing input modalities. Yeah. Well, to be clarified, so these are just four types of interactions: redundancy, uniqueness in the first and second, synergy. They're not always going to be there. So in the sarcasm, you're going to have a lot more synergy, right? If you're saying positive, negative stuff, there's going to be a lot more redundancy, right? Yeah. Oh, you're saying like, for example, in this case, where is that small amount of redundancy happening? So I always think of it as you can tell redundancy, sorry, you can tell sarcasm from what they're saying in language. And if you just look at only the expressions, you can also tell they're sarcastic. So both modalities separately indicate sarcasm, and together they also indicate sarcasm. And maybe there are settings like that. We've not looked at that, all the data points. But you can see that there's just very, very few examples. Yeah.
So I'm curious how you think about the lack of modality in these various settings. In particular, back in the context of, in some cases, that modality won't exist at all. In some cases, we have selected.
So I think about lack modalities. Good question. I like to distinguish those when when the modality is there, but is not actively. So one example I'm thinking about that space is if you build a video model to understand a person, you're always going to be picking out what they say, what their expressions are. But how do you tackle the setting where they might be thinking something, but they aren't saying it? And that's really cool. In fact, some of my students are currently working on this data set of mimes. You know what mimes are? Charlie Chaplin mimes, right? And that's a cool example because I personally think once you have language in a lot of these, video-based human interaction, human communication settings, language will dominate. Language is informative. You have the best language models. The model won't look at other modalities. So we're building a MIME data set to exactly study this setting of how do you infer what a person is thinking, what a MIME actor is thinking when they aren't saying it. So that's doable through several data sets we're currently working on. If your modality isn't collected at all, like if you just don't have a microphone to pick up someone's speech, then that is of course more challenging. Several ways I can think of, off the top of my head is we've been doing this interesting work in trying to use cross-modal translation to impute missing modalities. If you never have a microphone to pick up what you're saying, you can perhaps use the words and your facial expressions to infer what your sound would be like had there be a microphone. So cross-modal translation is a way. I think other folks are also in this field trying to impute missing modalities, so that could be an option as well. Cool.
dynamic setting is that thing. So possibly have like with also a taking a picture of the modality, take one modality, different modality, say you want to get the modality, simply kind of take them on, learning to kind of take with giving modality to the modality. Well, I guess you can say why can't modality, have to do that still,
Well, so you're saying as modalities come in, just open up new adapters, open up new parameters, right?
yeah, in a way like, yeah, tokenizing modalities and then that, so that
You could, that could be interesting. I think the only worry there is that if you don't have multiple modalities coming in and you're not modeling the interactions, then you're only going to be learning unimodal to transformer. You're not going to be learning the multimodal interactions between your input modalities, right? So you could have vision, image to transformer, language, audio to language, sensor to language, right? You wouldn't be modeling the fusion of the different video, audio, and sensors together. Yeah. So one thing we're working on right now is I skipped in this I skipped in the context of time, but working on some of these mixture of experts models that is able to automatically discover when you should be opening up a new set of parameters for fusion if there's some informative information to be discovered, and otherwise you're not going to be opening up new parameters. Yeah. So I think mixture of experts also a way towards tackling that. Right. We're doing something like this. Yeah.
Like, for example, so there's something like, just do something like that. But, but for that, based on the presentation, I think,
I agree. Spatial reasoning is difficult for multimodal models. We didn't cover spatial reasoning too much today, and this is something that I'm thinking about, haven't really worked on. I think a lot of times it is usually about more data. How do you give the data to the model that is actually compositional, that has difficult cases of spatial reasoning? I know there's a ton of work people who are doing in terms of compositional models that actually compose the different parameters in a way that respects the reasoning. Yeah, I mean, not something we've really worked on, but it's a good question. Yeah.
Yes. When you took a lot of problems, from my sensors, they run into the problem of causality. And I did find some interesting things where experience that's it has high synergy,
Mhm.
but it's not necessarily explainable.
High synergy, but not necessarily explainable. Yes, I mean, a lot of the best methods designed to learn synergy are essentially learning more complex interactions between modalities, right? You have a multiplicative interactions at first order, you have polynomials, you have tensors, you have transformers, and learn more and more complex interactions. So in fact, the more synergy you're trying to learn, the less explainable you will be. How to make it more explainable? We've had some work in this space. I can highlight very quickly. I've been developing things that are able to interpret multimodal models. So I think a key idea here that we did was this idea of second order gradients. You take a first order gradient from your label prediction to your language, and a second order gradient from the language to the vision. That tells you how these two features are interacting with each other. So they're interacting in the same positive direction. It's redundant. If only one of them has a gradient and the other one is zero, second order gradient is zero, that's unique. And if they're interacting in different directions, it's synergy. So there are ways to do it post hoc. How to do both synergy in the modeling and interpretation is hard, just like any problem in interpreting neural networks from a functional perspective. It can be hard, but it's a good direction to work on. Yeah. Yeah. Right. Right. So the fact that if something is missing, that can be an indicator of a person's health, right? That's true. So as I mentioned, that's one of the things we're kind of working on, this, dynamic modality. We've not formalized it too much, but I'm sure there's a ton of stuff to be done in this direction. The idea that if something is missing, it can be a big indicator is pretty important as well. Yeah. Yeah.
Kind of the knowledge of the past, why would you from what you can thoughts about how these ideas could be generalized, centralized knowledge is classifying more.
Interesting. So the first part of the talk does require you to define a why. It does require you to define what is a task you're trying to predict. It doesn't yet extend towards unsupervised settings. But separately, we have some work on improving contrastive learning. So as you know, contrastive learning only requires X1, X2. You're learning features, which can then be fine-tuned towards Y. We've studied multimodal contrastive learning, not in the same context, but a slightly different context. But as of this information theoretic framework requires you to know what the label is. Yeah, I can point you to the works. Right. Thanks, everyone.